Okay, here we go. So today's date, let's see, November 30. So our objective today really is to find arc length and area of a sector, okay? And I kind of drew some pictures. Okay, arc length is just an arc. It's part of a circle. So the formula should be part of a circle, right? So arc length is actually part of a diameter. I'm sorry, part of circumference. So it's really part of the circumference So if I look at my formulas on page 263, I've got two different formulas. One is in terms of degrees, and then the other is in terms of radians. Now before I write them down, look how simple the one is in terms of radians, right? So the whole reason is that radians are connected to the arc length, right? So our formula for arc length it's if you take a portion, which is our circumference, which is 2 pi r, and we also have to convert that out of a circle, so then you can have what portion of a circle, theta over 360 degrees. What you have is what fraction of your circle is circumference. Now I like to reduce the 2's because it seems silly to have a 2 and a 360 in the same formula. So I just reduce it down to just pi r theta, or theta times pi times r over 180, okay? For the arc length. So if I look at example 1, all right, example 1, I want to find the arc length. Okay, so I'm looking at the length of this arc, right? Just going to use my formula. And the symbol S, they like for arc length. I do not know why. I suppose I'm not going to use A because that looks like area, but they'll use S for arc length. And then I'm going to take 110 over 360, because that's what portion of the circle is, times my pi times my radius, okay? And I'm just going to use my, Lauren? What's that? I reduced the 2, right? Oh my goodness, Ellie, thank you. 180. Oh my goodness. I need to pay attention to what I'm doing. Thank you. Thank you, thank you, thank you. So I'm just going to use my calculator. 110 divided by 180 times my pi times my 6, and my arc length is about 11.52 centimeters. Okay, pretty easy. And thank you, Ellie, for my mistake. Okay. Now, if it's in terms of radians, there is such a simpler formula. So if it's in radians, just S is equal to R theta. But theta has to be in radians, which already has the conversion in there anyway. So if it's in terms of radians, the arc length is just going to be S equals our radius times our angle, okay? So radians are so much easier. And it shows the connection. So we'll use this one later, but let's go to the sector of a circle. So the sector of a circle, if it's in degrees, they like the symbol K. So again, it's what fraction of the circle, and then the area of a circle is pi r squared. Here's my area of a circle, and what fraction of that have. So the formula makes sense to me. Pi r squared, area of a circle, and what fraction of that circle do you have? So, yeah, so it would be, as far as area, we'll go K is equal to theta over 360 times pi r squared. And they like the symbol K for area. I don't know. It's just the way it is. So in example 1, let's find the area of the sector. Now, of course, the area is how much is inside. It's not a length, it's an area, so we'll use this formula. We'll go S equals theta, which is 110 degrees, over 360 pi times the radius squared. Right? So I'm just plugging the numbers into the formula. Pretty easy. I mean, a kid in geometry could do this, right? Except for the radian part. That you don't know about that. 110 divided by 360 times pi times 6 squared, and I get an answer of about 34.56, about 34.56 centimeters squared, because it's area, right? Now, if it's in radians, it's so much easier, okay? So the area of a circle, of a sector in radians is just this 1/2 r squared theta. Now, that's a pretty simple formula in comparison to the other, right? So the area is K is equal to my 1/2 r squared theta, okay? So I've got some formulas now, and I can just use them. So to do this lesson, it all depends on only one thing. Is it in terms of radians or in terms of degrees, all right? So example 2, a sector of a circle has an arc length of 6, area of 75, find the radius and the central angle. Now, example 2, we don't know anything about theta, right? We don't know anything about theta. So we've got really two choices, because it doesn't ask us to find it in degrees or find it in radius. It's up to us. Do you want to find that angle in radians or in degrees? Okay, we do degrees. Radians is easier, but we'll do degrees. So if you want to do it in degrees, we know a couple of things. We know that it has an arc length of 6, okay? All right, so, and an area is 75, right? So if I have to find the radius first, let's take a look at possibly my arc length formula. So my arc length formula is theta pi r over 180, right? Well, that's too many variables, isn't it? How about if we do it in radians? I've got S equals r theta, right? And what I know is I can put the 6 in for the arc length. I don't know the radius or theta, right? Too many variables. Sorry, you guys. I should pay attention to what I'm doing, okay? So I use my arc length formula. Put the 6 there. But I don't know the radius or the angle, right? But I have a second piece of information, that's the area, right? So the area is 75. I've got an area formula which is my 1/2 r squared theta, right? I know 75 is my area. 1/2 r squared theta, all right? Well, I could solve for r and plug that in for theta, right? Or I could solve for theta and plug that in for r. I could do either one. Doesn't really matter. I guess I'll solve for r. R is equal to 6 over theta, right? My 6 over theta in for r, right, in for that, right? So I'll have a 75 equals a 1/2, substitute 6 over theta squared times theta. How am I doing? Or I'll have a 75 equals 1/2 times 36 theta squared times theta. Okay, I'm running out of room, but I'll scoot it up here. So let's make this a little bit easier. I'm going to multiply by 2. You okay with that? Just simplify, let me multiply by 2, and I'll put 150 here. is equal to, and I'll cancel a theta for a theta, so I'll have a 36 over theta. Right? All right, what I multiply by 2, cancel a theta for a theta, so I have a 36 over theta. And then theta would equal 36 over 150. And I'm just going to use my calculator to get that answer, okay? Clear. Let's see, what is 36 divided by 150? It should be a nice decimal. Yeah, 0.24. So my angle theta is 0.24 radians. Okay, now what if I want the radius? Okay, now this is getting easier now. I can put this 0.24 over here and I can get the radius. Okay, so I'm going to go 6 divided by 0.24. My radius is 25. Okay, so 6 divided by 0.24 is 25 is my radius. All right. Now there's one more formula that we probably could have done this a little bit easier. Hey, the book gave us a formula that would have made this much easier.
Nice.
And there it is. It gives us a formula with area, and there's no theta with R and S. So I could have gone and used this formula first without having to do all that work. Does that make sense? Let me write this formula down. So there's also a second area formula, and we're going to put that in right here. K can also equal 1/2 R times S. And I put it in the middle because you don't need to know the angle. Which would have made this problem a lot easier, because then you could have gone 75 equals 1/2 times R times the arc length with a 6, and you got the radius pretty easily. And then once you get the radius, you can get the theta from using that formula. Would have been much easier, okay? Can you turn the page? Okay, example 3. A sector of a circle has an area of 25 centimeters and a central angle of 1.5 radians. Okay, now we've got something here. So radians, right? We've got an area, so I've got a K, and I've got a central angle, I've got a theta. So what I do, here's what I know. These are I've got a K, and I've got a theta, and I want to find the R. So I want to find R, and I want to find S. So this is the way I like to do this. I like to write down all the variables. So then I can look at the formula, right? Look at all, okay, I know K, I know theta, I want to find R, S. So then I look at my formulas, okay? So if I flip my formulas, and I want to find theta, and I want to find R, right? So let's see here. K and theta. Here's my K and theta's here, right? I know those two, which means I could find R, right? I know the K and the theta, I could find R. So let's use this one first. Does that make sense? So I'm going to write down my first formula is K is equal to 1/2 R squared theta. I think that's my formula. Yes. How did I pick that? I knew the K, I knew the theta. That formula is going to work nicely. I can find R. Am I making sense? Okay,
Yeah.
good. Am I, Carly?
Yeah.
So I found this, I know these two. I found a formula with those two in it, right? So let's go 25 equals 1/2 R squared times 1.5. Now I can find R, can't I? Let's multiply by 2 first. I'll make that a 50 equals a 1.5 R squared. Divide by 1.5. What is it, 75 now? No, it's going to be smaller than that. 33 1/3. Square root, right? Oh, Bill, stop that. Square root answer. So the radius is about 5.77. Now, arc length. So I got to find S. So what do I know? I know the radius, I know theta, I know the area. I need to find S. So I look at my formulas. Which one should I use? Yeah, how about that one, right? Let's use that one because I know R, I know theta, so it's going to be pretty easy. So my S, my arc length, is just going to be my R times theta. S is equal to my radius, which is 5.77, times my theta, which was 1.5. I'm just going to go 5.77 times 1.5. My arc length then is about 8.655 centimeters. So in centimeters, okay. Okay, now, this is drawn way out of perspective, so let me see if I can draw it on the board. Really much better, okay? Let me see if I can draw it, okay? Now, you've got to think about this gigantic circle. Gigantic circle that has this radius, okay? You with me? And it's drawn way out of proportion, right? But as a really easy little, like, estimation, this arc length of the gigantic circle, this little itty bitty arc length of this gigantic circle is almost the diameter, right? Does that make sense? Can you see that? Like this little piece right here, even though it's an arc length of the big circle, it sure looks like the diameter of the little circle. So if we find the arc length right there, it's kind of like the diameter of the planet, right? Does that make sense? So it says the apparent size. Now the apparent size is the angle, right? Little itty bitty angle. Remember, this is not drawn to scale, right? Little itty bitty angle. You're looking at a planar way up there. It's like this big, right? It's the apparent size. So the apparent size is 0.01 degrees. So obviously not drawn to scale when it's closest. And yet the distance is 8 times 10 to the 8th kilometers away. What's that? 8 billion? Yeah, 80, no, not 8 billion, it would be 800 billion. 800 billion kilometers, 800 billion, right? 800 million. 800 million! Oh my goodness, I'm a math teacher, I'm so embarrassed. So look at this, here's our arc length. Let's just put this down. So let's find the arc length of the gigantic circle, right? So if we find the arc length of the gigantic circle, S equals theta over 180 pi times, yep. Isn't that my formula? Pi r, right? Pi r, because it's in degrees. So this would give me the arc length of the gigantic circle of this itty bitty arc length, which is basically the diameter of the planet, right? So I'm going to go, okay, S equals 0.01 degrees over 180 pi, and the radius is this 800 million, right, Lauren? 800 million. Or we just put 8 times 10 to the 8th power. Let's see what the size of it is. 0.01 divided by 180 times pi times 8 times 10 to the 8th power. So I've got about 139,626 kilometers for the diameter. Okay, how's that? Yeah, I think it makes sense when I try and draw the gigantic circle in there, right? And then you can kind of see how it can look like a diameter even though it's a piece of an arc length, right? Okay, that's all I have.